Hello again. We are continuing our discussion on how derivatives can be applied to real-world situations. And today we're going to talk about how we can use derivatives to figure out some of the properties that a curve has before I actually graph it on the XY plane. So let's get started. To kind of cheat a little bit and show you what's going on, I've given you a graph and I'm going to give you the function for that graph. The function is 1/3 x cubed minus a half x squared minus 2x. Okay, so I want to know over what intervals is that function increasing and over what intervals is it decreasing. All right, well, I could easily read that from the graph, but let's pretend that I didn't have the graph right now and continue on. So I know that the function is going to be increasing whenever the first derivative is greater than 0. So when the first derivative is greater than 0, what that means is that the tangent lines all have positive slopes. So if you can imagine looking at any point to the left of x equals -1, you can imagine drawing a tangent line on that curve and it would have a positive slope. Okay, and similarly, the function is going to be decreasing whenever that tangent line has a negative slope or whenever the derivative is less than 0, however you want to say it. All of those things mean the same thing. All right, so let's figure out. What I want to do is, first of all, I want to figure out when is the first derivative equal to 0. Okay, well, I take the derivative and I get x squared minus x minus 2, and I want to know when is that equal to 0. Well, luckily this can be factored into x plus 1 times x minus 2. So when is that equal to 0? It's equal to 0 when x is -1 and x equals 2. Okay? So those are the only two places where the derivative is going to equal 0. Everywhere else, it's either going to be greater than 0 or less than 0. Okay? So those red dots there are the only places where the derivative is 0. All right, so what I'm going to do to figure out where it's increasing and where it's decreasing is create a sign diagram. Okay, so here's what it looks like. Because there are two x's where the derivative is equal to 0, I need to create three sections on this sign diagram because my breaking points in the number line are at -1 and +2. So I need to consider three sets of x's. Okay, there are the x's that are less than -1, there are the x's that are between -1 and +2, and then there are the x's that are bigger than 2. All right, and I want to know what's happening with the derivative in each of those sections. Okay, so for the first section, I'm just going to take any random number that I want that's less than -1, and I'm going to plug it into the factored form of the derivative. And I just want to see what sign I'm going to get. I don't really care what the value of the derivative is. I only care whether it's positive or negative. So think of any number that's less than -1 and plug it into that factored form of the derivative. If you plug it into the first factor, you will get a negative number. And if you plug it into the second factor, you will get a negative number as well. So no matter what x you choose that's less than -1, you will get a negative times a negative, which is positive. So the derivative is positive everywhere from -∞ to -1. Then as I move to the second region, if you think of any number that's between -1 and 2, and you plug it into the factored form of the derivative, the first factor will now change sign and become positive, but the second factor will still be negative. So the derivative takes on a value that is a positive times a negative, which is negative. And then going to the third section of the number line, any number that's bigger than 2. So pick any number that's bigger than 2, plug it into the factored form of the derivative. The first factor will stay positive, and the second factor will now become positive. So I have a positive times a positive, which is positive. So now I can see everywhere where the derivative is positive and everywhere that it's negative, knowing that it's only equal to 0 at -1 and 2. All right. So what that means is anywhere that the derivative is positive, I know that the original function is going to be increasing. And anywhere that the derivative is negative, the original function will be decreasing. So I now know, based on this sign diagram, that the function is increasing from -∞ to -1 and from 2 to +∞, and it's decreasing on the interval from -1 to 2. And if you look at the graph actually supports that statement. So I know that I've done my work correctly. All right. This leads us to a discussion on what stationary points are and what inflection points are. Okay. So if I find the derivative and I set it equal to 0 and I solve and I find those x's, well, those x's don't tell me very much except where to divide the sign diagram. Because when I do have a derivative that equals 0, I do know that there's a horizontal tangent line, because that means that the tangent line has a slope of 0, which means it's horizontal. But that could mean one of three things. It could mean that there is a maximum at that point, as you can see by the green dot and the green tangent line. There could be a minimum at that point, as you can see by the blue dot and the blue line. Or there could be an inflection point, as you can see by the red dot and the red line. Okay, so in the case of the first one, the green one, the function is switching from increasing to decreasing. For the minimum, the graph is switching from decreasing to increasing. And then at that point of inflection, it's not really changing. It's decreasing before the red dot, and it's decreasing after the red dot. So it just stops momentarily and then keeps going in the original direction that it was going. That's what an inflection point is whenever the tangent line is 0. We call that a horizontal inflection point. Okay, but we'll talk about that a little bit later. So here's an example. We need to find and classify all the stationary points. So all of those points where the first derivative is equal to 0 on this graph. So I have y equals x cubed minus 3x squared minus 9x plus 5. And I'm not going to give you the graph for this one. So we're going to have to figure it all out by hand. The derivative is going to be 3x squared minus 6x minus 9. And if I factor that, I get 3 times x plus 1 times x minus 3. And I'm going to set that equal to 0 to figure out where my stationary points are. Well, to solve that, I get x equals negative 1 and x equals 3. This allows me to figure out how to sort out the sign diagram. So the sign diagram is going to have 3 sections again, one where the x's are less than negative 1, one where the x's are between negative 1 and 3, and the last one where the x's are bigger than 3. So same process as before. I'm going to pick some x that is less than negative 1 and plug it into the factored form of the derivative. When I do that, the first factor is going to be negative, and the second factor is also going to be negative, meaning that the entire derivative is going to be positive. Then as I switch to the second section, picking some number between negative 1 and 3 and plugging it into those factors again, the first factor is going to switch from negative to positive, but that second factor is going to stay negative, meaning that the derivative is going to be negative everywhere between negative 1 and 3. Then I move on to the last section. Pick a number that is bigger than 3, plug it into the factored form of the derivative. The first factor will stay positive, and the second factor will become positive. So that means my derivative is 3 times a positive, so the whole derivative is going to be positive. Okay? So I know what the derivative is doing, and so what that means for the function is everywhere before x equals negative 1, the original function is going to be increasing. Everywhere between negative 1 and 3, the function is going to be decreasing, and then everywhere after x equals 3, the function is going to be increasing again. So remember what I said before about classifying these things. If a function switches from increasing to decreasing, what that means is there must be a maximum at that point. And then if it switches from decreasing to increasing, there must be a minimum at that point. So what that means is there's a maximum at negative 1 and there's a minimum at 3. And as you can see, that's what the function actually looks like. All right, last example. We're going to do the same thing with x to the 4th plus 16x to the 3rd plus 72x squared plus 7. The derivative is 4x cubed plus 48x squared plus 144x. And if I factor that, I get 4 times x plus 6 squared. Okay? If I set that equal to 0, then I know that the solutions will be x equals negative 6 and x equals 0. So here's my sign diagram. I split it at x equals negative 6 and x equals 0. So the 3 sections are where x is less than negative 6, where x is between negative 6 and 0, and where x is bigger than 0. So let's look at the first section. Plug in any number that's less than negative 6. The first factor will be negative, and the second factor, because it's being squared, will always be positive. So the derivative for all x's less than negative 6 will be negative. Then if I move on to the second section, pick any x between negative 6 and 0, and it will still be negative, nothing has changed. And then when I pick an x that is larger than 0, only the first factor will change and the second factor will stay positive, again, because it's being squared. So the whole derivative is going to be positive for all x's that are greater than 0. So what do I have? Because the sign didn't change at -6 from decreasing to anything else, that means that I have an inflection point. Since it did not change from negative to positive or positive to negative, I call that an inflection point. And then for the second part, because it does change from decreasing to increasing, I have a minimum at x equals 0. Okay, so there is a point of inflection at x equals -6, and there's a minimum at x equals 0. And if I actually draw the graph, that's what it looks like, and that kind of supports that statement. Okay, so there's a lot of information here. We'll do more tomorrow. If you have any questions, please let me know, and I will see you tomorrow.